Hello. This video includes information on introduction to reaction rates.
Chapter 17 looks at what we call chemical kinetics. So when we talk about chemical kinetics, it's essentially the study of reaction rates. Okay, it answers questions like how fast are reactants used up? Or how fast are products produced? Or maybe we know the initial concentration of the substance and we want to find out what the concentration of that substance is after a given amount of time. All of that is incorporated into what we call kinetics or chemical kinetics. So when we look at chemical kinetics, it looks at how reaction rates change under various conditions. So we'll change conditions and we'll see how the rates of the reactions change. And it'll also deal with the molecular events that occur in the overall reaction. So we're going to look at how does the concentration affect the reaction? How does the temperature affect the reaction? And those all are part of this chapter on chemical kinetics. So let's look at rates of reactions first. When we talk about a rate is a change in something per unit time. When we look at rates, a rate is the change in concentration. These brackets here mean concentration. A is just a generic reactant. So the change in the concentration of a reactant over the change in time. It's kind of like when you drive down a highway, you talk about your rate of speed being 65 miles per hour. Okay, your change in distance over your change in time. This is the same kind of thing. Okay, it's a rate. How much does the concentration change per unit of time? And the rate depends on what the reactants and the products are, what the concentrations of the reactants and the products are, and the conditions that the reaction takes place in. So what temperature does the reaction occur at? Do we have a catalyst that we add to the reaction? All of these things affect the rate of a reaction. How do we measure rates? Well, there's different ways that we can measure rates depending on what it is that we're studying. Okay, if we're talking about gases, what we could do is we could measure how the pressure changes over time, or how much the volume changes over time. If we talk about colored compounds, maybe the reactant is colored and the product is not colored, we could measure the change in light absorption over time. And that could tell us the rate of the reaction. Or maybe the reactants are electrolytes, which can conduct an electric current. We could use conductivity to determine the rate of the reaction. So depending on what the reactants and the products are, will determine the way that we measure the rates of the reactions, or the way that we measure how much the concentration of something in the reaction changes over a period of time. When we talk about solutions and we look at reactants and products in a solution, we're going to be using concentrations in terms of molarities when we look at reaction rates. So we know that molarity is moles per liter. So the moles of solute per liter of solution is what we'd be using when we look at solutions. So let's say we have this reaction here. We have hydrogen peroxide, and it decomposes into water and oxygen. And we want to look at the rate of this reaction. Well, the rate of decomposition of this hydrogen peroxide is the change in the concentration of the hydrogen peroxide over time which we could rewrite as the final concentration minus the initial concentration. That would give us our change in concentration over the final temperature minus the initial temperature. That would give us the time. That would give us the change in time. Or we could write it as a real shorthand and say the change in the concentration of hydrogen peroxide over the change in the time is going to give us the rate of decomposition. Now, this is important. Oh, sorry, this gets cut off on the bottom. These are all negative values. And the reason they're negative values is because the amount of hydrogen peroxide is going down over time because it's decomposing. So the concentration after a period of time is going to be less than the initial concentration. So the rate of a reaction with respect to reactants will be negative values because the reactants are being consumed. Products will be positive values because they're being produced. So when we talk about the units, they could be moles per liter per second. It's one way it could be written. Or since liters is in the denominator, we could say moles per liter second. It's just another way of writing the same thing. And since moles per liter really means molarity, we could write it as molarity per second. So all of these are different ways that we can write the units for the rate of a reaction when we're looking at solutions and we talk about things in terms of concentrations. So let's look at some data. So we have this hydrogen peroxide in a container, and time zero means we're just starting the reaction. And we measure the concentration at 0 hours. And then we measure it after 6 hours. And then we measure it after 12 hours. And then we measure it after 18 hours. Now, look at the units for a second. This says moles times liters to the -1 power. Anything to the -1 power is a reciprocal. So this really means moles per liter. Again, it's just another way of writing the units for the concentration. The concentration actually changes during this time period. And to figure out how much it changes, we would just subtract the two, final minus initial. So during this 6-hour time period, the concentration changes by -0.500 moles per liter. Okay, the negative sign because we're consuming hydrogen peroxide. So if we go from 6 hours to 12 hours, the concentration goes down again, but the concentration goes down less during this time interval than during the first time interval. And then if we were to look from 12 to 18 hours, again, the concentration is going to go down again. And if we were to look from 18 to 24, it goes down even more. Now, the time period is the same. The reason the concentration isn't changing as much as we go down the table is because we've got less and less of the reactant to react. Essentially, the reaction is slowing down as time progresses. So to calculate the rate of the decomposition of the hydrogen peroxide, we would take the change in concentration and divide it by the change in time. So -0.500 divided by 6, there actually should be a negative sign here. These should all have negative signs. -0.0833. And then after the next time period, -0.0471, and then -0.0208. The rate is going down as the reaction progresses because more and more of the reactant is being decomposed. The less reactant we have, the slower the reaction goes. And these are average rates because they do vary within this time period. We're just finding the average rate of change for this time period, and then the average rate of change for this time period, and then the average rate of change for this time period. What's happening to the rate? The rate's going down because the concentration of reactant is decreasing as the reaction progresses. So let's look at this graphically, and there are two things we're going to look at. When we talk about instantaneous rate, it's the rate at an instant in time, or it's the rate at a specific time during the reaction. And oftentimes we talk about the initial rate of the reaction, and that's just the instantaneous rate at time equals 0, or the instantaneous rate as the reaction just starts to proceed. And that's good for comparing different trials. So if we wanted to graph the change in the concentration of the hydrogen peroxide over time, we would see that as time progresses, the concentration of hydrogen peroxide goes down. And that makes sense because the hydrogen peroxide is reacting. Now, if we wanted to look just at 12 hours and find what the rate is at 12 hours, that would be an instantaneous rate. And if we wanted to talk about the rate right at time equals 0, just as the reaction's beginning, this would be the specific instantaneous rate that we call the initial rate. So this is our initial rate of reaction. And when we look at the instantaneous rate can be calculated by taking the tangent at the particular time that we want to study. So if we wanted 12 hours, we would draw a line tangent to the curve at 12 hours, and then take the change in concentration over the change in time, which is essentially the slope of this graph. And that would give us the instantaneous rate at that particular time. Now, rates are relative. So how do the rates of the reactants and the products relate to each other? Well, it has to do with the stoichiometry of the balanced equation. So let's say that we're talking about the decomposition of ammonia into nitrogen gas and hydrogen gas. Well, if we were to look at the graph of that, we've got concentration along the y-axis and time along the x-axis. At time equals 0, we only have reactant. Okay, the reaction hasn't started yet. So hydrogen and nitrogen are both 0. And ammonia is some value. Now, as the reaction proceeds, the ammonia reacts and the concentration of ammonia goes down. As the reaction proceeds, the concentration of nitrogen and the concentration of hydrogen go up because we're producing nitrogen and hydrogen. If we came up with the instantaneous rate, let's say we were going to pick a time, so we pick 500 seconds, and we want to calculate the instantaneous rate of hydrogen and the instantaneous rate of ammonia and the instantaneous rate of nitrogen, we would get these values here. Now, it's the change in concentration over the change in time. And we get 2.91 times 10 to the minus 6 for our hydrogen, 1.94 times 10 to the minus 6 for our ammonia, and 2.91 times 10 to the minus No, that's not right. 9.70 times 10 to the minus 7 for our nitrogen. Now, over here in this table, I just rewrote the rates and I made them so that their exponents are the same. Makes it a little bit easier for us to compare these numbers. You don't necessarily have to do that, but I made them all 10 to the minus 7. So the instantaneous decomposition of ammonia at 500 seconds is 19.4 times 10 to the minus 7 moles per liter per second. If we were to look at nitrogen, nitrogen's being produced at a rate of 9.70 times 10 to the minus 7 moles per liter per second. And hydrogen is being produced at a rate of 29.1 times 10 to the minus 7 moles per liter per second. Now, these numbers aren't the same because the coefficients in the balanced equation aren't the same. If we were to look at, let's say, ammonia and nitrogen, the rate of production of nitrogen is half the rate of decomposition of ammonia. 19.4 divided by 2 gives us 9.70. Well, that makes sense because if we were to look at the stoichiometry between ammonia and nitrogen, it's a 2-to-1 ratio. So ammonia is being consumed at a rate twice the rate of nitrogen. Now, if we were to look at hydrogen, hydrogen is being produced at a rate 3 times the rate of nitrogen. So 9.70 times 3 would give us 29.1. Again, that makes sense because when we look at the stoichiometry in the balanced equation, nitrogen is a 1 and hydrogen is a 3. So hydrogen is going to be produced 3 times faster than nitrogen is. So the balanced equation tells us the rate at which, relative rates, at which the reactants react and the products are produced. Now, there was a question in the chat, will we ever have to solve for the rates from the graph or would the values be given to us? You would never have to draw a tangent and find the slope of that line. You're going to find that value other ways anyway. This is more like a kind of question you would be given other than, trying to find a tangent on a line and calculating the slope of that tangent. So if the rate of decomposition of ammonia at a particular temperature is 2.10 times 10 to the minus 6 moles per liter per second, or molarity per second, what is the rate of production of nitrogen and hydrogen? So we're just going to use the stoichiometry in the balanced equation. So let's look at the first one. We'll do that one together. So we write down what we're given. We have 2.10 times 10 to the minus 6 moles per liter per second. There's the concentration of our ammonia. The balanced equation tells us we have a 2-to-1 ratio of ammonia to nitrogen. Well, we want to cancel out ammonia and go to nitrogen. So we're going to put the 2 on the bottom and we're going to put the 1 on the top, meaning that the ammonia will be decomposed at a rate twice the nitrogen being produced. So the rate of production of nitrogen is 1.05 times 10 to the minus 6, half of the consumption of ammonia. So using this as a model and starting with the rate of decomposition of ammonia, calculate what the rate of production of hydrogen would be. Okay, so when we look at the balanced equation, for every 2 moles of ammonia that are consumed, 3 moles of hydrogen are produced. It's a 2:3 ratio. We're getting it right from the stoichiometry in the balanced equation. So if the rate of decomposition of ammonia is 2.10 times 10 to the minus 6, the rate of production of hydrogen is 3.15 times 10 to the minus 6 moles per liter per second, or molarity per second. So let's see if we can do this. We're given a reaction. Okay, it's the oxidation of ammonia, so it's a different reaction. We've got some maybe more complicated coefficients there. It says if the rate of formation of nitrogen is 3.5 moles per liter per second, what is the rate of disappearance of ammonia? So again, model it like the last 2 problems we did. Start with what we're given. Make sure you label what it is. Use the balanced equation to come up with your conversion factor from nitrogen to ammonia, and figure out what the rate of disappearance of ammonia would be in this reaction. So we're given 3.5 moles per liter per second of production of nitrogen. It's a 2:4 ratio. We really should put a negative sign in here because the ammonia is being consumed. So -7 moles per liter per second for the ammonia. So we've talked about what reaction rates are. We know that they are relative to the stoichiometry in the balanced equation. Now we're going to talk a little bit about some factors that affect reaction rate. So one of the factors will be what the reactants actually are. Okay, some reactants are very reactive, some reactants are not, just by the nature of the reactant themselves. So as an example, P nitrotoluene is here, and 2,4,5 trinitrotoluene is here. This is TNT. TNT is very explosive. P nitrotoluene is not reactive, just by the nature of their reactants. Okay, the state of the subdivision of the reactants. Well, what does that mean? It just means the surface area. If you increase the surface area of the reactants, you're going to increase the reaction rate. So if we have iron powder here being added to hydrochloric acid, and then we have an iron nail here, the rate here is going to be much greater than here because there's a greater surface area. Increase the surface area, you increase the contact of the reactants, which increases the rate of the reaction. Temperature affects the rate of a reaction. Typically, reactions occur faster at higher temperatures. And the general rule, is that for every 10-degree increase in temperature, we're going to double the rate of the reaction. Concentration of the reactants. Okay, usually the concentration affects the reaction in a direct way. As we increase the concentration, it increases the reaction rate. And the reason for that is we're increasing the chance, the likelihood, the probability that reactants are going to come in contact with each other. The more we have, the more likely they're going to come in contact with each other, and the faster the reaction will go, the higher the reaction rate will be. And then if we were to add a catalyst, that affects the rate of the reaction. Okay, catalysts are substances that typically increase the reaction rate, and they do that by lowering the activation energy, or lowering the minimum amount of energy that's required to get the reaction going. And catalysts are not part of the reaction. They're not consumed during the reaction. They're there at the beginning. They're there at the end of the reaction. So overall, they are not consumed during the reaction. And maybe in your biology classes, you've talked about biological enzymes. Those are just a type of catalyst.